Good morning, everybody. I hope everybody had a wonderful weekend. Today, we're going to continue forward through section 10.2. This is our last full week of class. And then next week, we have Monday and Wednesday, and that's it. That's it. You're at really the end of the course. And that works very nicely because we're almost, well, I wouldn't say almost, but we'll be done with 10.2 today. And then we have 10.3 and 10.4, and that's it. So we're pretty much on time. Just to remind you where we were going through calculus with parametric curves. So we had, I had recommended that if you need the review, watch the review of parametric equations video that I have there. And then we go into all the calculus you ever learned with parametrics. Let me turn off the ding dongs. Ding dong, ding dong. There we go. And so we started with this idea of what is, if I gave you a parametric curve, how could you find its derivative? And that way we could talk about how would you find the tangent line for a parametric curve at a point or something like that. And yes, I am still grading exams. Actually, I haven't even started grading your exams. I have 2 other sets of exams I'm in the middle of grading. So the nice thing about the derivative for a parametric curve is it's pretty easy to remember. You know the derivative is dy dx, that's the Leibniz notation. And so you just essentially, visually, divide numerator and denominator by dt. So dy dt over dx dt, where y is a function of time and x is a function of time. So that's what we went through last time. And we only did a couple quick examples. So I mentioned that horizontal tangents will occur when the numerator of your derivative, which is dy dt, is 0, as long as dx dt is non-zero. And vertical lines occur when dx dt is 0, where dy dt is not 0. So we mentioned that last time. And then we went through an example of find an equation of the tangent line to a curve at a or at some given point. And that's what we did there. And at the end of class, we visualized that using Desmos. It's very nice to use Desmos for visualizations. And we'll probably do that throughout lecture here. All right. So let's continue forward. This is example 10 to number 2. And this is still using derivatives. So let's consider the following. You're given the parametric curve defined by x of t is equal to cosine of 2t, and y of t is cosine of regular old t, where t goes from 0 to pi. I'm not going to bother graphing this out. Instead, I'm going to do the mechanics. Unless they ask me to graph this out, then I'll graph it out. So if I find dy dx, so basically find the derivative of the function, and find the second derivative, and determine the values of time for which the curve is concave up. Very fast problem. So we're going to go ahead and jump right into it. Dy dx, again, is dy dt over dx dt. Y being cosine of t, so the derivative of the cosine is just the negative sine of t. X, where are you, x? Being the cosine of 2t. So that'll be the negative sine of 2. Well, actually, it's negative 2 sine of 2t. And then what you should do, if you can, is do a little simplification. Whenever you see a trig identity, use it. Well, and also if you have 2 negatives there, right? So let's cancel the negatives. You know that's sine of t over 2 sine of 2t, but sine of 2t is twice sine cosine. So it's going to be 4 sine of t cosine of t. It's just very helpful. And then you can cancel the sines as well. And so this will be 4 times 1 over cosine, or 4 secant of t. That would be the derivative. And then the second derivative, just to remind you, that's kind of the one that a lot of people foul up on a little bit. The second derivative of y with respect to x is, well, the derivative with respect to x of dy dx. But luckily we know that dy dx is just that secant of t, right? And so what we're going to do is we're going to say that's the same thing as the derivative with respect to x with respect to time, of, and I'm going to color code this, make it a little more obvious for all of us. It's the derivative of dy dx with respect to time divided by dx dt. It's the same actual definition as the derivative of a function with respect to x. It's just that your function is not y, it's actually dy dx. And so when you take the derivative of a function, again, it's derivative with respect to t of that function over dx dt. So that's a good way to think about it. And how did the 4 go to, I don't, because 2 times the 2 here is 4. Oh, how to go to the numerator. I thought you said denominator. How to go to the numerator. It isn't. That's in the denominator. I'm completely lost. All right. Mistake number 1 of the day. There we go. Thank you for catching me on that. Now what we're going to do is go ahead and take the derivative of this dy dx with respect to t. So derivative of that with respect to t is going to be 1/4. Derivative of the secant is secant tangent. So secant of t, tangent of t. And then again, you divide that by dx dt. We know dx dt is actually just going to turn into 4 times the sine of t times the cosine of t. That is because, again, the derivative of x is actually a -2 sine of 2t. And we know that that's going to simplify down because we've already done it to a 4 sine of t cosine of t. Now cleaning this up, that'll be a 1/16. I'll at least do that piece. Secant is 1 over cosine, but we have another over cosine right there. So we have a secant squared of t. Tangent is sine over cosine, but we have a sine downstairs that will cancel with that. Oh, geez, mistake number 2. Thank you. The 4 would be a negative. Man, my brain is just not on today. All right. Yeah, sorry about that. Thank you. Everybody keep me honest. I apologize. So that dx dt, because I didn't really kind of go through it, I just barreled through. Derivative of that cosine is a -2 sine of 2t. And when we did that, the reason why we didn't have the negative there was because it canceled with the negative upstairs. However, you're absolutely right. We should keep that negative downstairs. We don't have a negative upstairs here to cancel with. So it'd be a -1/16. Perfect. And again, tangent is sine over cosine. That sines will cancel. So we have a 1 over cosine again, which will make this a secant cubed. And that is completely done as far as dy dx and the second derivative of y with respect to x. That's what they asked us to do. But then this part A is actually fairly compound because they're saying determine the values of t for which the curve is concave up. So we want to know when is the second derivative of y with respect to x positive. Let's go ahead and answer that question. I'm going to write that question in blue here. When is the second derivative of y with respect to x positive? And if you take a look at that, that's really basically asking when is -1/16 secant cubed of t, when is that positive? Multiply both sides by a -1/16 or -16, sorry, and you'll get secant cubed of t is going to be less than a -16. Again, multiplying both sides by, oops, damn me, it's 0. Multiplying both sides by 16, it won't flip the sign until you multiply both sides by negative. That flips the sign. Obviously, 0 times anything is still 0. And so you want to know when it's secant cubed less than 0, which is not such a terrible question to answer. That's the same thing as asking when is secant less than 0. And we know just by looking at the secant, which is the reciprocal of the cosine, right? So the cosine kind of looks like this. You can see it goes less than 0 at pi over 2, or from pi over 2 to 3 pi over 2, from negative pi over 2 to negative 3 pi over 2. So if they restricted the quadrants, it would be a little bit easier to answer this question. So I would say it this way. If they restricted to be on the interval from 0 to 2 pi, then we know that the time values for which our curve is concave up, which is when secant of t is less than 0, occurs when t is in the interval from pi over 2 to 3 pi over 2. If you want to put it in general, oh, was it given from 0 to pi? Perfect. Oh, thank goodness. From 0 to pi. Perfect. Then it's just from pi over 2 to pi. And you can actually include the edge point there, although technically it wouldn't be. Normally you wouldn't have to include that. But yeah, it's from pi over 2 to pi. Thank you. I didn't even recall this being restricted. That's perfect. That way I don't have to come up with some type of long-winded restrictions or formula for all the odd multiples of pi and all that fun stuff. All right, thought I'd get all my mistakes out of the way, so let's go ahead and now continue forward. Find any points where the curve has horizontal and vertical tangents. So this entire piece right here was part A. Now we're going to part B. I think they speed up as we move forward. So part B, find any points where the curve has horizontal. Let's worry about horizontal tangents. So here's the deal. If you take a look at this, let's take a look at the derivative here. So this is the derivative, the first derivative. To have a horizontal tangent, or sorry, let's actually horizontal. To have a horizontal tangent, we want dy dt to be 0. However, we do not want dx dt to be simultaneously 0. So, oh, and it's not including. That's why you said that. Sorry. Alyssa's telling me the endpoint was not included in that pi, and she's absolutely right. So when you take a look at this, if we had simplified, or if we didn't simplify, maybe I should say it that way, we get to this point, you can see that actually it looks like dy dt is 0 at any integer multiple of pi. However, dx dt was also going to be 0 at those same exact values. And so therefore you cannot say they're horizontal tangents. Luckily, after simplifying anyway, you don't actually have to worry about it. There's no way 1/4 of the secant of t, which is how I'd normally like to write that. There's no way 1/4 secant of t is going to be 0. So I happen to know dy dt, dy dt is not going to be 0 when dx dt is not 0. So that's probably a good way of saying that. So for the horizontal tangent, we need dy dt to equal 0, but dx dt cannot also be 0 simultaneously. That is never going to happen. Will not happen. Try my W again. This implies no horizontal tangents. Now, vertical tangents, yes, there are going to be vertical tangents here. So let's go ahead and go to vertical tangent lines. That implies dx dt must be 0 again, but dy dt cannot be simultaneously 0. Again, I explained it last time. If they're both 0, that means that you're not moving that Etch-a-Sketch dial. You're not moving actually either of them. So the point is not moving at all. So there's no horizontal or vertical tangent because you're not moving in either direction, either vertically or horizontally. So you can't say that you just have a point in space. It's not going anywhere. So that can't provide a vertical or horizontal tangent. All right. So let's go ahead and find out when is dx dt equal to 0. Luckily, we know what dx dt is. It's technically negative 2 sine of 2t. I'll just write that just to be careful. Which means that we would want the sine of 2t to be 0. Which means we'd want 2, well, actually, oh, yeah, I'll write it that way. We want 2 sine of t, cosine of t to be 0. You don't actually have to do it this way. You could have said, I want 2t to be a multiple of, integer multiple of pi. But there's something I want to showcase here. And obviously that implies that sine of t is 0 or cosine of t is 0. Now, here's the problem. We can't include the pieces where sine of t is 0 because that's where dy dt is also 0. So I'm going to cross that out and I'll write that down. I'll just point an arrow out. This occurs when dy dt is also equal to 0. And we don't want that to happen. So we have to throw those out. But the cosine of t being 0, that's fine. The numerator, dy dt, is not 0 when the cosine of t is 0. It's 0 when the sine of t is 0. And so as long as we don't have a sine of t being 0, we're okay. Cosine of t is 0 at t equals pi over 2. On our interval in question, it's just going to be pi over 2. Normally, it'd be pi over 2 plus pi k. But again, on our interval, it's only going to be pi over 2. Box that up. That will be when we have a vertical tangent at time pi over 2. So that was part B. Find any points where the curve has horizontal and vertical tangents. Points. Well, since I said points, I suppose I should go ahead and list out the x and y values for that point. So this is just something that is a minor detail, but if somebody does say, hey, I need the point where this happens, you have the time right now where that happens, but you don't actually have the point. To find the point, you're going to plug those time values in for t in the x of t and y of t right there. Sorry, I was just taking a drink there. So x of time pi over 2 is cosine of twice pi over 2. Cosine of pi, which is a -1, and y at time pi over 2 is cosine of pi over 2, which is 0. So the point is at -1, 0, where we have a vertical tangent. All right, and let's see, what else do we know about this curve, or what else are we being asked? Find the equation of the tangent line at pi over 3. I don't know if you guys can see that. I'll zoom in. Find the equation of the tangent line to the parametric curve at time pi over 3. This just is a repeat of what we were just doing, right? So we just found the derivative at time pi over 2. Now they're asking us, find the derivative at time pi over 3. Very fast work here. I'll write C right here. So for a tangent line, just like back in Calc 1, you need, not a line. You need two things. You need a point and a slope. So the point, x at pi over 3 and y at pi over 3, it's going to be cosine of twice pi over 3. which is pi over 6, which is root 3 over 2. And y at time pi over 3 is cosine of pi over 3. Wait, twice. Did I write twice pi over 3 is root 3 over 2? It's not. It's a negative 1/2. I was thinking pi over 6 for some reason. Twice pi over 3 is 2 pi over 3, and that would be negative 1/2 for the cosine and a positive 1/2 for the regular old pi over 3. Sorry about that. Yeah. So we got the point. It's at negative 1/2, positive 1/2. Now we need the slope. The slope is going to go ahead and be dy dx. And this is kind of a nice notation to use with a pipe here. Dy dx evaluated at time pi over 3. And we happen to know that dy dx, we computed it out, is just 1/4, wait for it, the secant of t. So I'll plug in 1/4 secant of pi over 3. Now, the secant of pi over 3 is 2. So that's going to be 2/4 or 1/2. A lot of halves going on here. So the equation tangent line is just y minus the y value is equal to the slope times x minus the corresponding x value for the point. And you can clean this up. 1/2 x, let's see, plus 1/4. And then we're going to add 1/2 to both sides, so that's plus 3/4. Now, I have a propensity, obviously this morning specifically, of making a ton of mistakes. So let me go ahead and just showcase this curve using Desmos and then graphing that tangent line at time pi over 3 so that we can kind of get a feel for what this curve looks like. The fact that it is the y value is the cosine, that means that, and this is sort of me answering, analyze what happens between time equals negative pi to time equals positive pi, even though negative pi to 0 is not in the domain of the stated function. Well, if you take a look at this, the cosine from time negative pi to positive pi, that's what the cosine looks like. So really you can visualize that the y values are going to start low, go high, and then go back down to low. That's really what they're going to do from time 0 or negative pi, sorry, to time positive pi. They're going to go low, climb up, and go back down. Now, I don't know what that's my Etch-a-Sketch for my right knob. That's my right knob Etch-a-Sketch, the one that controls the vertical values. I know they're going to start low, climb up, and go back down. Okay. But the X values are a little bit different. And if you watch my video on parametrics, then you already know the punchline to this. But so we know that cosine of 2t goes twice as fast as a regular cosine of t. So normally the cosine of t does that from 0 to 2 pi. However, because it's going twice as fast, because that 2, it does this from 0 to pi. And therefore it does that same thing from negative pi to 0. And so what this is telling me is this is my time axis, and this is my technically x axis because it's the output for that function. It's telling me that my x values at time negative pi start, I should probably, you have to imagine rotating this way and then flipping it about the t-axis. If you had a piece of paper, the way you would do that is you would draw this down on a piece of paper, then you'd turn it 90 degrees counterclockwise, or you could turn it technically 90 degrees clockwise. Yeah, you could do that too. You could either turn it 90 degrees counterclockwise or 90 degrees clockwise, but in either case, in the end, you're going to flip it. So I suppose I could go clockwise here. If you turn clockwise 90 degrees, you're going to flip about the t-axis in the end. And so in the end, your graph is going to look like this. So at time negative pi to time positive pi, your x values are going to do kind of crappy drawing. Sorry about that. Do something like that. So I happen to know that this is the x value axis. I happen to know that my x values start over to the left, and then they go over to the right. Sorry, that's right. They start over to the right, and they go over to the left, come back to the right, go back to the left, go back to the right. That's kind of how you could graph it out, sort of. It's not really the easiest way of doing it, but that's how you could graph it. It's going to look like a figure 8, I think. But let's go ahead and check this out on Desmos. I'm going to head over to Desmos really quickly. And meanwhile, I'll take a drink here. All right, over at Desmos. I'm going to go ahead and turn off the grid. It's never very helpful. There we go. And to graph a parametric, I mentioned it last time, you just put in parentheses and you type in the x function cosine of 2t, end the parentheses, and do the y function, which is cosine of t. And then you have to do it from time value to time value. So we were asked to do from negative pi to positive pi. No, not even that. So what's interesting about this is that it doesn't actually, maybe I would like to do this. Let's see if I could do it this way. I just want to showcase what this is going to look like. So I'm going to do this. I'm going to put in a cosine of 2a, comma, cosine of a, and I'm going to add a slider to a, and the slider to a is going to go from negative pi to positive pi. This is so you can see 0.01 how this is going to go. So give me a moment. All right. So this is time where this dot is right here. That's time negative pi. As it goes from time negative pi to time 0, it's done that. That's the path of travel. From time 0 to time pi, it retraces itself. And this is actually a good example because parametric curves can retrace themselves. And so you have to be very, very careful about that, especially if I were to ask the arc length of this curve. If you were to try to compute the arc length and you went from negative pi to pi, you would actually double count the arc length. So you have to be very careful about that. You want to make sure that you graph it out to see, does it actually retrace itself? You don't want it to do that. And you can see why the original domain restriction said go from 0 to pi, because if you went from 0 to pi, you're only getting one full cycle of the curve. That's it. And also note that at time pi over 2, which is halfway through, we have a vertical tangent. We would have a vertical tangent if I graphed it in there. And then the other thing I wanted to note was that we wanted to take a look at and verify that y equals 1/2 x, except the x has to be there, plus 3/4 was a tangent line to this curve at time pi over 2. So let's go ahead and put a at time 3 pi over 3. And yep, there it does look like that at time pi over 3, that point, the tangent line is the line that we just created. That works beautifully. So Desmos can be a very powerful tool to verify what you're computing. Graphing this by hand, I probably wouldn't even have you graph this by hand. This is not one that I think is a typical one people should be able to graph by hand. It's not a favorite of mine. So anyhow, you could use Desmos to graph that out. Or if it was, for example, an exam, I would say, this is the graph of this parametric curve. Please graph that, or find the slope of the tangent line at this, or whatever it may be. Let me share my screen back here. All right. So that almost rounds out derivatives of parametrics, but we have one last little example here. When asked to find the tangent lines or tangent line or tangent lines to the parametric curve x of t, which is this business, t to the fifth minus 4t cubed. Again, this is something I wouldn't expect you to graph by hand at all. And y equals t squared. If you were asked to find the equation of the tangent lines, or yeah, that's exactly what they're asking. The equation of the tangent lines to the parametric curve at the point 0, 4. That is critical because this is an x, y point. That's a Cartesian point. So this is x, y, not t, something, but x, y. We first need to find the value of t that will land the function at that point. Let's just go ahead and demonstrate this process. We're not going to bother with finding the equation of the tangent lines because we've already done that in 2 separate problems. So how would you find out when, that's the time question, when will our curve strike the point x equals 0, y equals 4? Well, it is as simple as allowing x to equal 0 in the first equation and y equal 4 in the second equation. It's, I should say, sort of that simple. There is a caveat here, and so we'll see it in this example. So we need to solve this and this. But we need to solve these simultaneously. That is, both equations have to simultaneously be satisfied. So in the first equation, you get this. 0 is equal to t cubed times t squared minus 4, which tells us the solution to the first equation is either t equals 0 or t equals plus or minus 2. The second equation, that tells us t is equal to plus or minus 2. What does that mean? It means that our y value is going to be a height of 4 at time 2 and negative 2. Our x value will be 0 at time 2 and negative 2 as well, but also at time 0. But at time 0, our y value is not 4. So I'm going to throw out the time 0 value because while it is true that x does become 0 at time 0, its corresponding y value is not 0. It's not 4, sorry. Its corresponding y value is not 4. In fact, I'll write it here. At time equals 0 implies x is 0, which is what we wanted, but y is equal to 0, which is not what we wanted. But at time plus or minus 2, we definitely get that x is equal to, I'll actually write this one in green. At time equals plus or minus 2, we get that x is equal to 0 and y is equal to 4, which is exactly what we wanted to get. So we will have 2 tangent lines. Now you may say, wait a second, how can you have 2 tangent lines? You may or may not. You may already know why you can get 2 tangent lines for a parametric curve. Parametric curves are very unique. They are functions of time, not of x and y, but of time. And if you were to go to Desmos and just quickly graph this out, because you would not want to graph this by hand, t to the fifth minus 4t to the third, comma, t squared. Okay. I'll zoom out here. Oh, and I have to get enough time values in here. So let's go from time -4 to time +4. This is that parametric curve from time equals -4 to time equals +4. Let me just graph a to the fifth. When I graph a to the fifth minus 4a to the third, what it's going to allow me to do is it knows that a is not a typical variable like t is. And so it's going to allow me to add a slider so I can see a point on this and I can track its progress. It's a very nice way to just see which way is my curve going and all that fun stuff. So here we go. I'm going to zoom out a little bit further so you can see the point. Where the heck is that point? It might be, let's not start at -4. Let's start at -3 to +3. I think that point is still way out there. Yeah. Okay. So you can see at time -3, that point's way over there. As you increase time, I'll just zoom in. Once time gets really close to -2, here's time -2. You see that point, it crosses the y-axis. That's not that important. However, you also see that the parametric curve crosses itself there. So there are two tangent lines right there at 0, 4. One for time equals -2. And as we said earlier, one for time equals +2 right there. Very, very neat curve. By the way, also very neat. Notice that the point there, in fact, let me press play, and I'm going to slow it down significantly and then go back. Okay. I want you to notice something about parametric curves, is that as you plot points, the speed with which you're plotting points changes. So notice that thing is slowing down. I'm not slowing it down. It's just that when parametric curves get plotted out, they have certain speeds associated with how quickly their points are being plotted, or speeds with which the curve is being carved out. So as time goes on, this curve will actually get carved out faster and faster and faster. You'll see it happen here. So very, very neat idea with parametrics. I kind of dig parametrics for that reason. They just have a lot of neat features to them. I'm going to share my screen back on my laptop here. A lot of switching back and forth between laptop and desktop when you're dealing with parametrics. All right. So the only point of that example was just to make sure that you knew how to find the corresponding time values for specific points. Not too terrible. So what else did we do when we went through calculus? Well, we did limits, but you don't do limits with parametrics, so you don't have to worry about that. But we did derivatives, so we covered that. Then we started dealing with areas underneath curves, and that's what we're going to deal with here. Areas underneath parametric curves. Same idea as areas underneath regular curves. So start with the assumption that x is a function of time and x is a function of time and y is a function of time. It's just x is equal to, we're going to call it f of t. That's what this is. And y we're going to call g of t. They're both functions of time. Well, we know the area underneath the curve normally is the integral from x equals a to x equals b of the y value dx, right? You're taking, let me write this down so you can see why, you know that why that's true, but I'm just going to say it. It's heights times widths, right? These were all rectangles. So you're adding up the product, or you're adding up a bunch of areas of rectangles is basically what you're doing. But y, so this is a great way, if you ever forget how to find the area underneath the parametric curve, you should never forget this. And if you know y is some function of t, well, let me go ahead and color code this. If y is g of t, then that's what you'd replace y with. If x were some other function of t, let me wait for my screen to catch up. Okay, so if x were some other function of t, then dx is just f prime of t dt. And that's where this comes from. It's a very fast derivation. That's the actual proof, by the way. So very, very fast derivation. Now notice the limits of the integral. So when you're finding the area underneath the curve in terms of y and x's, it was going from x equals a to x equals b. Here we're going from time equals alpha to time equals beta. This time equals alpha, I'll zoom into here, is the time associated with x equals a. And that time equals beta is the time associated with x equals b. And that's how I'm going to write it here at first. Time associated with x equaling a. Same thing up here. Time when x is equal to b. What's going to be weird for you when you do these problems is that it turns out, well, you should know that if x is equal to f of t, then if x is equal to f of t, and somebody said, oh, by the way, x is equal to a, then t is f inverse of a. In other words, the time when you start your integral is going to be f inverse of a. So we call that time alpha. Alpha will be f inverse of a. And then the time where you end your integral will be the time when x is equal to b, and that's f inverse of b. What's interesting about that is it may be the case, even though you may have been integrating from x equals 1 to x equals 10, that might be time values of, let's say, 17 to negative 12. In other words, your time values may be going backward. What's important here is that you're integrating from x low to x high. In fact, it's so important, I'm going to write that down. Warning. Make sure you are integrating from x low to x high. Just like you normally would, right? I integrate from 1 to 10, not from 10 to 1 when finding the area underneath the curve. If you go backwards, you're going to get a negative area, and that will not make sense. By the way, the same holds if you're integrating with respect to y. Y low to y high. So that's just a heads up. Just treat it like it's a normal integral. Set it up like it's a regular old integral. And then when you switch into the world of time, ignore the fact that the time values may go from high to low. That's okay. The integral will still work out. So we'll see that in an example, I think. Let me take a drink here. So my warning up above here before we even start is you want to be careful with parametric curves because they can retrace themselves. And I even said that in our previous example, thereby giving the illusion of larger areas or arc lengths than actually exist. And the question always comes up, how the heck will I know if my parametric curve retraces itself? Often it's very difficult to tell. But there's some ways that you can tell your parametric curve is not going to retrace itself. So I'm going to give you kind of the clue that this parametric curve is not going to retrace itself. Since e to the t is always increasing, x is always increasing. This implies no retrace. There's no way it's going to retrace. Try to put your pen on a piece of paper and let your x values go to the right. Your y value could be whatever you want it to be. Will it ever retrace? The answer is no. It'll never. To retrace, you'd have to start going backwards. And that's not going to happen because the x values are always increasing. So that's a great way to know that your curve is not going to retrace very quickly. The times where I kind of worry about retracing is when we have sines and cosines. That's when I go, oh, shoot, that might just retrace. So those are where you're going to have to be careful. I would recommend just using Desmos to see if it retraces. That's probably the easiest, fastest way to do that, honestly. Okay. Find the area enclosed by the x-axis and the following curve. All right. So this one will require us to actually graph We do not by hand, but via Desmos, because this is just convoluted enough that graphing by hand is not going to be worthwhile. So in the homework, I'll try to make sure that I let you know, like, you will have to use Desmos to graph these, right? So let's go ahead and just quickly view this graph in Desmos, and then we'll come right back here and finish it out. So let me share my screen. You guys don't know it, but there was a time when Desmos didn't exist. So let's see. The x value is 1 plus e to the t. And the y value is t minus t squared. Okay, so notice it does this little itty-bitty piece right here. I'm going to go ahead and just make it from -10 to 10. Just so that we can see. Because Desmos automatically does it from 0 to 1. But from -10 to 10, you can see that curve just keeps kind of going on forever. We want to know, what is the area underneath the curve that's enclosed by the x-axis in the curve. So we want to know, what is it from this point right here, right there, all the way to this point right here. And you're not going to use Desmos to find those x values because it'll be decimal approximations. So you're going to actually use your mathematics to find those values. So let me showcase how that's done. But visually, I hope it's okay. You can see we want to find the area from x equals 2 to x equals whatever that number is, maybe 3.75 or something like that. And the question is, how the heck am I going to do that? How can I go about finding what those x values are? And the simple answer is solve that first equation, or second equation, sorry, y of t is equal to t squared minus t minus t squared. Solve that if y is 0, because you want to know when you hit the x-axis. So let me write that down. To determine when the curve strikes the x-axis, let y equals 0 and solve. Not too bad, because this equation, letting y equal 0, is pretty easy, right? So if you let y equal 0, you get t minus t squared there. You can factor out the t, and you get that this y is equal to 0 at time 0 and time 1. All right. Well, we need to integrate. Remember, we're finding the area underneath the curve. The area goes from x equals something, low value though, to x equals something, high value, please, of y dx. Well, let's see which of the x values are low or high here. So at time 0, that implies x is equal to 1 plus e to the 0th, or 2. When time is equal to 1, that implies x is equal to 1 plus e. So it turns out the time is flowing along with the x values, which is perfectly fine. That's okay. But just don't expect it to always be that way. It could have been the case that when you plugged in time 1 or 0, sorry, it could have given you a larger x value than when you plugged in time equals 1. No matter what, you're still going to go from x low to x high. So when I look at these, I notice that this is the low x value. This is the high x value. So those are the ones I'm going to fill in here. Just like that. That's how it's done. So I know I'm going from integrating from x equals 2 to x equals 1 plus e. I know my curve, if you were to draw it out, looks sort of like that, from x equals 2, to x equals 1 plus e. And now I'm going to go back to the parametric curve, because I don't want to solve this for t and then plug it in here and then make y a function of x and try to integrate that. Instead, I'd like to just integrate this parametric curve, find the area underneath it. So I'll change this to time values. X equals 2. is associated with time 0. X equals 1 plus e is associated with time 1. Y is t minus t squared. That's what y is. And dx is the differential of x right up here. Dx is just going to be e to the t dt. It's the derivative of that right-hand side dt. So we'll have, write this in e to the t and then dt. And you would integrate that to find the area underneath the curve from time 0 to time 1. It's actually not going to be bad. And in fact, a good review for your final exam. Anyway, it's a by parts integration. You're going to choose one of them to be u and the other one to be dv. Obviously, I think you know you're going to choose u to be this and dv to be that. Start taking derivatives. That's 1 minus 2t, then a negative 2, then a 0. This is always e to the t, e to the t, e to the t. You're going to add the product of these two, subtract the product of those two, add the product of those two. In fact, I should have used red here. There we go. So when you do this integral, you're going to add the product of t minus t squared e to the t, evaluated from 0 to 1. And then you're going to subtract the product of 1 minus 2t e to the t, evaluated from 0 to 1. And then you're going to add the product of negative 2 and e to the t, again, from 0 to 1. Very fast by parts integration. If you plug in 1, you'll get 0. If you plug in 0, you get 0, at least in that first term. So that's gone. You plug in 1 here. You get 1 minus 2, or negative 1, times the negative is positive 1, e to the 0th, or e to the first, sorry. If you were to plug in 0, you would get 1 minus 0, but and it actually has a positive in front of it. No, wait, hold on, give me a moment. Minus. Okay, minus 1 minus 0, so that's going to be a positive. Positive, and then e to the 0th, which is 1. I do much better if I write it out like this. Oh, it's 1 minus 2, and then you have also minus 1 plus this. Yeah. Oh. That's a minus. I shouldn't rush through this one, actually. Let's see. Do it this way. 1 minus 2, e to the first, and then minus 1 minus 0, e to the 0th. That'll be a minus, a negative e, minus 1. That's a 1 plus e. Oh, I did have it right. Good for me. Yay. Good for me. All right. And then finally, the last one, which is a minus 2e to the first, and then a plus 2e to the 0th. And then you can combine like terms. 3 and minus e. That's a positive area, so that should make sense. So this is how you would find the area underneath the parametric curve. They're actually not too bad. Areas underneath parametric curves are pretty okay. The main thing to note is that you need to go from x low to x high, always. Unless you're integrating with respect to y, which you'll go from y low to y high. But your time values may go backwards. Just be aware of that. This is one of my favorite styles of problems because, well, it just allows me to really use Desmos and see kind of a cool parametric curve. So let's go ahead and just showcase this, and then we're going to find the area, the leftmost loop of this chain. Okay, so let me go ahead and go back to Desmos very quickly. A lot of Desmos here. Now we were asked to graph x of t is equal to t squared minus 5. Y of t is equal to sine of t. And we're asked to do this from t equals negative 20 to positive 20. And then they actually gave us a window as well. They said let the x value for the window go from negative 5 to 400. And the y value for the window go from negative 5 to 5. There we go. So it's a really kind of a neat, almost a helix type of curve. And we want to find the area underneath this leftmost loop. Now, the area of this, don't think it will cancel. We actually want to find the entire enclosed area here, not this positive area, and then we will subtract off this negative, or then we'll lose this negative area, which gives us a 0 area. That's not true. You'll have a very positive area there. So you could easily just find the area underneath this upper hoop or upper loop here, and then just double it up. But our goal really is, just like last example, find out when are the y values 0 here, and then I'll find their corresponding x values. So that's what I'm going to do. I'm going to set this up. I'm going to ask myself, when are the y values 0? And then I'll try to find the corresponding x values. Hopping back here. All right. So we've seen the curve. I mean, if you want to graph it out, you can. It kind of does this. Okay. And we want to find the area of this leftmost loop. So we're going to let y equals 0, because when y is equal to 0, we'll get all of these points right here. All the time values where you cross the x-axis. That will be when y is 0. So we'll have an infinite number of options. However, once we have that infinite number of options, we just want to find the most negative of those corresponding x values. You'll see this. It actually is not too bad. So letting y equal 0, we get that 0 is equal to sine of t. Or in other words, our loop crosses the x value when t is any integer multiple of pi. Okay. Now that I know that, I'm going to ask myself, well, what's the lowest possible x value, considering that these are my time values? So when is x the most negative? Well, if you think about it, try to plug in any integer multiple of pi. Let's list out a few integer multiples of pi, like negative 2 pi, or a negative pi, or 0 pi, or 1 pi, or 2 pi, right? These go on forever in both directions. But if you were to look at this x function and try to plug in any of those values, the only one that will give us the most negative value is times 0. I'll highlight that. I'll say x at times 0 is going to be 0 squared minus 5, or negative 5. If you try to plug in any other integer multiple of pi, you're going to get like pi squared minus 5, which is going to be positive. So I happen to know that this x value, the leftmost x value there, is going to be negative 5, well, the point is negative 5, 0. The time value for that, maybe I'll actually zoom out and allow myself to write this a little bit larger so you can see my thought process. That point is negative 5, 0. It occurs at time equals 0. And now it's my choice to find out when is the next most positive, or not most positive, when's the next x value. So at x equals negative 5, we cross the x axis. But what is this next x value where we cross the x-axis, that'll occur either at time equals pi or time equals negative pi. I'm just going to plug in time equals pi, and we'll get pi squared minus 5. That point right there is pi squared. It's supposed to be a pi squared minus 5 comma 0, and it occurs at time pi. If you want to know which way it carves out, what happens with the y values? Think about a sine curve. That's what the y values are. The y values will start to climb and then fall. So this is the way it's carving out as x increases. I can see that there's a slight delay between when I'm writing something on my screen and that it appears. So I'll try to look up every once in a while and pause. But because I know it's carving out like that, I know that it's giving me the upper half of that curve. So I'm going to go ahead and say the area of first loop is actually not just the area of from x equals negative 5 to x equals pi squared minus 5. It's going to be twice that area underneath the curve. It's going to be twice this area right here. I'll wait for my screen to catch up. There we go. It's going to be twice that area. So I want twice that area. The area starts at x equals negative 5. It ends at x equals pi squared minus 5 and y dx. Now we happen to know when we switch into the world of t, oops, there should be a 2 in front of there, by the way. When we switch into the world of t, time equals 0 is associated with x equals negative 5, and time equals pi is associated with x equals pi squared minus 5. The y value is sine of t, I think. Yep. And dx is going to be 2t dt. And we have yet another by parts integration. This one's a little bit faster. So this will be 4 times the integral from time 0 to time pi of t sine of t dt. Again, building a quick table. T 1 0 sine of t, negative cosine of t, and negative sine of t. Add, subtract. So this will be 4. Don't forget the 4 because I often might. We'll add the product of t and a negative cosine of t. And we're going from 0 to pi. And we'll subtract the product of 1 and negative sine of t. So that's actually a positive sine of t. From, again, 0 to pi. It'll be 4 negative, and we get pi cosine of pi minus 0 cosine of 0. Notice I'm being kind of with this. I'm taking my time because I have a propensity. I'm human, just like everybody is. So I will make sign mistakes. This one I'm not concerned about. Sine of pi is 0. Sine of 0 is 0. So I don't care about that one. So this will be a negative 4 pi cosine of pi, but cosine of pi is a negative 1. So that's going to be 4 pi. That's the area of that inner, or the first loop, the leftmost loop there. really a very nice problem. You have to use Desmos or some type of graphing utility to help you visualize that curve. There's no way you want to do that by hand. All right, so we've done derivatives, we've done areas. I'm gonna highlight this, and because it's just going to be the same problem as before. So let me highlight that. I might come back to that, or I just might insert it as a video later on, because we've done a lot of areas. So I think it's time to move into Calc 2 material, arc lengths of parametric curves. Remember, the arc length function is, or the arc length that we generally, to compute the arc length, we add up all these little teeny arc lengths, little DS's. And DS was defined to be, actually it was proven to be, either, actually, maybe I should write it like this. Well, okay. Remember we did this, I'll do it this way. 1 plus y prime dy dx squared dx, or dx dy squared plus 1 dy. However, remember what that was built upon. You had some curve, and you had a wiggle in x and a wiggle in y. And this edge length right here we called a wiggle in s. And this floor length was a wiggle in x, and this was a wiggle in y. Using the Pythagorean theorem, we got that ds squared was equal to dx squared plus dy squared. And then we took the square root of both sides. It's a positive square root because s is an arc length, so that's always going to be positive. And we got down to this, although I had deltas, not d's, but that's okay. We can just kind of skip that for now. And then what we did to derive that black ink down there was we either divided out dx squared or we divided out dy squared. In either case, you get, in one case, you'd get the first black ink. In the other case, you get the second black ink. Another option we could have done, though, is we could have said, you know what I'm going to do? I'm going to divide both of these by dt squared. And obviously, that division by dt squared was not originally there. So you'd have to offset that by a multiplication by dt squared, which, when you factor that out of the radical, becomes dx dt squared plus dy dt squared, and then a dt. And that's the arc length function for, or that's ds for parametrics. Parametrics, actually, arc length is one of my favorite topics because of the fact that it's all about the Pythagorean theorem. It's really nice. So the arc length theorem for parametrics is just the integral of ds, just like we have been doing. And ds can be traded out for the square root of the Pythagorean theorem, essentially. Right? And your time values will go from time low to time high. Otherwise, you get a negative arc length because you're adding up. Think about it this way: you're adding up a bunch of positive values. That's what this square root is a positive value, non-negative value. So if you go from time low to time high, you're adding positive values in a positive direction. So you're doing, you have a positive arc length. If you were to go in the wrong direction, go from time equals -10 to time equals -20, then you're adding up a bunch of positive values, but in a negative direction. And positive times negatives, you're adding up a bunch of negative values. And so therefore, your arc length would be negative, which does not make sense. So always integrate from time low to time high when it comes to arc lengths. So I guess the punchline is this. With parametric integrals, all of them will go from time low to time high with the exception of areas. So I'll put that as a warning. And I think I actually have it as a warning in my lecture notes, but I'll just write it here again. The warning is parametric integrals go from time low to time high unless it's an area. Those go from X low to X high. And the time associated with X low might be greater than the time associated with X high in those cases. So that's just a heads up. So a good rule of thumb, just integrate from time low to time high unless you're finding the area underneath the curve. That's X low to X high. Okay. All right. So there's not much I have to do with parametric arc lengths. They're pretty fast. So I have a couple examples and then we'd be done with that. Notice there's my warning. In this case, time alpha must be less than beta, time low to time high. That's basically what that was. And again, you want to be careful with parametric curves because they can retrace themselves, thereby giving the illusion of larger areas or larger arc lengths. Now, again, I'm going to do my trick, which is I want to know, I'm afraid that this will retrace itself, but actually I could see that it's not going to, as long as either X or Y is always increasing or always decreasing. If either of those statements are true, then I know it's not going to retrace itself. Well, on the interval given 0 to 2, the X value is always increasing. Technically, the Y value is as well. So I'm going to go ahead and write that on the interval T going from 0 to 2, X is always increasing. Which implies no retrace. It's just if you're fearful of the retrace, that's a quick way to kind of allay any concerns, to make yourself feel a little bit better, like, okay, I don't have to worry about that. There's not going to be a retrace, so I won't have a situation that does this. You didn't see me do that, but that goes up to the top and then comes back down. Right? If I were to integrate, let's just say that was from time 0 to time 2, I would end up accidentally doubling up the arc length because I would have counted it twice. So that's just a heads up. That's a good way to quickly tell that you're not having a retrace, as if your X value or your Y value is always increasing. So now I'm just going to integrate. The arc length is just the integral ds. We're going from time low to time high of the square root of dx dt squared plus dy dt squared dt. These are really nice problems. I think parametrics end up being very nice for students because they're just super fast. So dx dt, for example, well, that's just 6t. We know squaring that's 36t squared. Dy dt, that's going to be, what's that, 6t squared? Yeah. So let's go ahead and insert that stuff in. Times 0 to time 2, square root of 36t squared plus 36t to the 4th dt. 36 will factor out. Square root of 36 is 6, so I'll at least put that up front. Also, square root of t squared will factor out. I don't have to worry about absolute values because I'm going from time 0 to time 2. So time is positive, or at least not negative. How's that? And now a u sub, right? U equal 1 plus t squared du will equal 2t dt. Okay, so let's see. That's going to be dt is going to be, well, at least I should say a t dt, and then 2 will be stolen out for du. And then we have the square root of 1 plus t squared, or in other words, u to the 1/2. When t is 0, u is 1. When t is 2, u is 5. And now I can just integrate. U to the 3/2 times 2/3 from 1 to 5. That's 2 times 5 to the 3/2 minus 1. Excuse me. Very nice, very fast, nothing really crazy. So this is kind of a nice way to finish out the course using parametric curves to find arc lengths and stuff like that. By the way, for those who didn't attend the integration B, this was like that was like the second integral, not the parametric part of it, but just this style of integral was the second one in the integration B. So anyhow, let's see. So that's a good arc length problem. And then this one. Okay, so this is somewhat nerve-wracking for me. Find the distance traveled by a particle with position x, y, as t varies from 0 to 3 pi for this parametric curve. X equals sine squared, y equals cosine squared. Now, this, and then it says, and then compare this with the actual length. That's the hint. The hint is that if you integrate from 0 to 3 pi, you're probably retracing. I know this is going to retrace. It's sines and cosines. You always run the risk of retracing with sines and cosines. Sorry, I'm just drinking my chai. Specifically, since sine squared of anything plus cosine squared of that same anything is equal to 1, this tells us that x plus y must equal to 1. That is, this is a line. So if you wanted to graph this, it looks like, I shouldn't use red. That's what it looks like. You might say, wait, that line should keep going, shouldn't it? And I would say, well, normally, yes. But x is sine of t, sine squared, actually. So it'll never be negative. X will never be negative because it's sine squared. And it'll never go beyond 1 because it's a sine. And y suffers from the same restriction. It'll never be negative. It'll never go beyond 1. So this parametric curve is literally just that little line segment right there. Nothing more than that line segment. So I know that if I were to try to find the quote unquote arc length from 0 to 3 pi, I'll likely retrace quite a bit. So let's go ahead and at least answer their question. A particle is traveling along this curve from time 0 to time 3 pi. If you want to see where the particle starts, plug in 0 for x. Oops, I don't have a pen on. Hold on. X of 0 would be 0. Y of 0 would be 1. So I happen to know that the particle starts here. This is time 0. Then you can plug in, let's just say x equals pi over 2. Let's do that. When x is pi over 2, you get sine squared of pi over 2, or 1. When you plug in pi over 2 for t in the function y, you get cosine squared of pi over 2, which is 0. So down here, this is time pi over 2. If you were to test a value in between, you'd find out that the particle traveled this distance. And then, using a different pen, I'll just showcase this. From time pi over 2 to time pi, it will retrace itself. I'm drawing it off to the side here, but I hope you get the point. From time pi over 2 to time pi, it'll retrace itself. And then from time, I'll go to blue here, pi to time 3 pi over 2, it retraces again. And you get the point. It just keeps retracing. Now, find the total distance that the particle traveled. Well, the total distance would be the integral from 0 to 3 pi. Oops, that's supposed to be a 3 pi. Sorry about that. Of the square root, basically, of the arc length, right? So square root dx dt squared plus dy dt squared dt. Now, I'm not actually going to integrate that because we're going to use a little trick here, but dx dt, let's go ahead and find out what that is. I'll write it up above here. So dx dt is going to be 2 sine cosine. I know what you're thinking. That's the sine of the double angle, but I wouldn't do that here. Dy dt is going to be a negative 2 cosine sine. I suppose you could technically. I guess you could do that as the sine of the double angle. You could do that. I thought that it would be slightly different, but no, you could totally do that as the sine of the double angle if you wanted to. So we know that if we were to set up this integral, it would be from time 0 to time 3 pi. Gosh, I keep wanting to write 2 pi. The square root of, again, dx dt, okay, we'll go ahead and write it as sine of the double angle. So it's a sine of the double angle squared. Plus, this is also the sine of the double angle, but negative. But when you square it, it becomes the sine of the double angle squared. Okay. And now you would normally integrate, but I'm not going to do that. The reason why I'm not going to is because I'm actually going to go and answer their second part. Find the actual length of the curve. Because then I can just say, well, if the actual length is, let's just say 1, it's not, but let's just pretend. Find the actual length of the curve. Then I would just multiply it by how many times we retraced. I hope you notice, if you're going from 0 to 3 pi, well, one length is half a pi. Then we have a full pi. So that's 2 tracings to get to a regular old pi. We want 3 of those pi's. So we're going to do 6 tracings here. So I know it's just going to go back and forth 6 times, essentially. There are 2 ways to do this. You can either use the fact that this is a 45, 45, 90 triangle. So that length is a root 2. And so the total distance would be 6 root 2. That's one way you could do this. The other way is to say, okay, well, then the arc length of that curve, we know it's going to be root 2, by the way. But if you want to use calculus, you could say, oh, it's the integral from 0 to pi over 2 of this right here, which is sine 2t times a root 2 dt. Now I'll pull out the root 2. 0 to pi over 2 sine 2t dt, and then integrate. And that's supposed to be a negative. But I'm going to pull that negative out front, actually, just because I want to. There we go. So you get a negative root 2 over 2. I'll leave it like that for the moment. Times cosine of pi is a negative 1. Right? It's cosine of pi because it's twice pi over 2. And then minus cosine of 0 is another 1. So you have negative 2 times a negative root 2 over 2, or in other words, root 2. But again, using the geometry is much faster. So the actual arc length is root 2, but the total distance that particle travels is 6 of those tracings. So it's 6 of those root 2s. So this is a good example of how a retrace would work. You just basically want to find out how much time it takes to go through a single tracing and not duplicate itself. That's a good way of doing that. All right, the last topic in this entire section is the last topic we dealt with when we were learning our Calc 2, which is surface areas. And nothing changes. It's the same thing. And this is beautiful about all this material. You're just going to get a lot of practice with arc lengths and surface areas. Remember, surface area is circumference times ds. Right? If you visualize it like this, you want to rotate that around. Well, if I want to paint the surface here, I'm rotating that through a circumference, and it has a little thickness, a little wiggle, and that's circumference times wiggle. There's no difference here. So watch what happens. I notice that theorem didn't tell us what the formula was because you don't need it. Again, my warning holds. It goes from T low to T high unless you're finding the area underneath a curve. But surface area, it's still T low to T high. Determine the surface area of this parametric curve. Super, super fast. That's why I can do it in the 3 minutes we have left. Surface area is circumference times arc length. Now I look at the problem and I say, is it parametric? Yep, it is. Okay, great. Well, let's see. I'm going to go ahead and say this is the integral 2 pi y. And I'm going to go ahead and integrate, the arc length, I'm going to do dx dt, dx d theta in this case, because they didn't give me a t, squared dy d theta, squared d theta. And we're going from times 0 to time pi over 2. There's no retrace, by the way, on this. I'm not going to bother showcasing it, but there's no retrace on this. From 0 to pi over 2, cosine is decreasing only, and sine is increasing only. So there's no retrace at all I have to worry about. I'll factor out the 2 pi times 0 to time pi over 2. The y value is a times the sine cubed of theta. Then we have the square root of, well, it looks pretty gnarly. Let's go ahead and take the derivative. What is dx d theta? Well, that's going to be 3a cosine squared of theta times a negative sine of theta. You look at that and you go, man, this is going to be a mess. It's not actually the case. It actually cleans up very nicely. Dy d theta is going to be 3a sine squared of theta cosine of theta. So we're going to square both of those and plug them in to our integral. When you do these problems, it looks worse than it actually is. So dx d theta squared is 9a squared cosine to the 4th of theta sine squared of theta plus dy d theta squared is going to be 9a squared again sine to the 4th of theta cosine squared of theta, and again d theta And just a little bit of simplification here. 2 pi, I'll factor out this a here. Integral from t equals 0 to t equals pi over 2. We have the sine cubed, and let's see what we can factor out of that radical. A 9, square root of 9 is 3. An a squared, square root of a squared is a, as long as a is positive, which I'm going to assume it is. Let's see, they both have a cosine squared in common, so I'm going to factor out the cosine. They both have a sine squared in common, so I'll factor out a sine. After factoring that all out, I'll be left with a cosine squared plus a sine squared. That is pretty beautiful because that is 1. I'll bring the 3 and the a out, so I get 6 pi a squared. We have a sine to the 4th of theta, cosine of theta, d theta. And then you would do a u sub and finish this out. U is going to be obviously sine, so it steals away a power of the cosine, and you'd integrate u to the 4th. Very, very nice problem. All surface area problems now you could do. They're really very, very, very nice. All right. So we have reached the end of lecture today. I will be back in about 10 minutes here for office hours. I hope you guys have a wonderful, wonderful, wonderful day. If I don't see you in office hours, then I'll see you on Wednesday. There's no quiz today. So have a wonderful day.